Hello everybody, today I'm going to be showing you my program which I call Cannibals. It's called that because these are little guys which kill each other and eat each other and basically reproduce like that. So um, basically the idea is that they have all of them have a brain which has some inputs about their neighbors and whatnot, and their brain is really just a neural network. And basically, every time, let's say we're looking at this guy and he killed a couple of guys there. So for those two guys that he killed, their brains will be copied from his. So basically, if you're a good killer, you'll produce more copies of yourself. And what that should mean is that, and also if you're good at surviving and avoiding getting killed, it also means that you'll survive long enough to make more copies of yourself. So just like in real life, it's a combination of your ability to get resources and just avoid dying in general. So it's sort of like natural selection. Another thing is that if you in this game, if you don't kill anybody for long enough, you will starve. And so every time you die of starvation, your brain gets copied from the guy here with the most kills. And so the whole system should evolve to having better killers and better uh, death avoiders. So the way that this works right now is that basically this is running at 60 frames per second, and you can see it. If I press P, at that point, if I press P, basically it stops rendering, and the whole program, the simulation, starts running much faster, about I think 1,000 times faster. It's about almost like about 100,000 times per second. The whole frame updates when you're doing it like that. So in that amount of time, it went from 9.5 million to 10 million frames. So basically, in that amount of time, it did about 500,000 frames. And right now, it's just going at 60 frames per second. So they learn much faster when you speed up the program like that and stop rendering. So yeah, basically, their brains are kind of simple neural networks. If you've ever seen pictures of neural networks, you'll know that they have layers, and well, not all of them, but in this case mine works with simple layers. There's the first layer, which is all the inputs, and in mine I have two hidden layers in between, and one final layer with three outputs. So the inputs, well, actually first I'll say the outputs. The outputs are, there's three of them: the angle that it should move in, the angle that it should point its stabby part. Those stabby parts they use to kill each other. The angle that it should point its stabby part, and the third one is the angle that they should move in the direction which is determined by the first output. So the first output could be, let's say, 45 degrees, and the second one could be 1, in which case they'll move at a speed of 1 in that direction, 45 degrees. And so yeah, they only have three outputs. Those are the ways that they should move, and it's actually not the velocity that they should move; it's the force that they should apply on themselves. So that's how they get the kind of smooth movement. But the angle that they output is very quickly changing and changes instantaneously based on their outputs, based on their inputs. And their inputs are their own angle, their own absolute velocity, measured with respect to just where they are in the screen, their own absolute velocity, and the relative x and y of their neighbors. So that's like 4 inputs right there, the x and y of each of their two closest neighbors. It always finds the two closest neighbors before getting the input from them for the neural network. So their neural network always has some input, and that input is the x uses its two closest neighbors. So yeah, the relative x and y of its neighbors, the relative velocity of its two closest neighbors, and the angle of its two closest neighbors. So when I first made this program, I thought, okay, well, they'll kill each other, and their brains will evolve to be better at avoiding each other and killing each other. doing both at the same time so that they can avoid dying but also get the most kills. It didn't actually work that well. Basically, what happened was that they all ended up streaming uh, across the screen, especially since there's like a left and every time. This is basically like a torus. This screen, it wraps around every time one leaves the left side. They come in from the right side, and same with in the vertical direction. So basically, they all ended up streaming across the screen because there was no cost to moving, or they didn't actually have to kill anybody. And if no one died, then it would never evolve towards better killers. If no one died, they would never die because no one was killing each other. So I had to add starvation, basically. So they all start off with a certain amount of energy every time one is created or copied from another guy. They start off with a certain amount of energy, and they lose a certain amount of energy based on how hard they're pushing themselves around, and they also lose energy just at a constant rate. So at the beginning of the program, you get to decide at what constant rate do you want them to lose energy. I'm just going to continue to run this at full speed. Yeah, what constant rate you want them to lose energy, and then what rate do they lose energy depending on how fast they move. So this was so that they don't just fly across the screen at full speed, because then they'll die of starvation, and they don't just stay still, because then they'll still die of starvation, just it'll take a little bit longer. So there's a constant energy and a movement energy, and yeah, once they die of starvation, they simply copy their brain from the best killer, and they get all of their energy back, but now they have a killer's brain. And yeah, so there's two ways they can die of starvation or by being murdered by somebody. If they're killed by somebody, and their brain is just copied from their killer. So the victim gets the brain of the killer. So in that amount of time, about a million, we're now at 11 million steps. There's been about 882,000 deaths. So yeah, as you can see, they get pretty good at avoiding each other and killing each other. It's pretty interesting. There's no visualization for the network, you can see, but basically it has 13 inputs, 3 outputs, and some inputs in between. Some layers in between. I think they have like size of 9 and size, I don't know, 6 or something like that. I forgot. It's on my other computer, but basically, yeah, they have these neurons, hidden neurons in between, and there's some connections which go between those neurons. And the way that it evolves is that every time they make a copy of each other, there's a small random mutation. Every time they get a copy of each other, one of their weights, a random weight, is chosen from their network, and it is altered by a random amount, close to 0, but not quite 0. It's basically like a normal distribution. And so they pick a random weight and change it by a small amount, and then they do the same thing for one of their biases. So if you know anything about neural networks, there's weights and biases, and that basically, besides the size of the network, that basically fully describes how the network works. And through those mutations, if the mutation is good for them, then it'll lead to them killing more and making more copies of themselves, and or it'll lead them to them surviving longer and therefore killing more and making more copies of themselves, and not also dying of starvation. And if that mutation leads to them dying of starvation or getting killed by another person or just not making enough copies of itself, then that DNA will not be passed on, or that network copy will not be passed on. So yeah, as you can see, if you ask me, it looks like they're moving pretty intelligently. They're kind of all keeping their distance, but still moving in every once in a while to kill each other. See, you might wonder why. Well, if the other guys got their back to you, why wouldn't you move in for the kill? Well, I think sometimes they trick each other. They put their back to their opponent, and that signals come and kill me, and then just before they come and kill them, they turn around and they stab them. So even when it looks safe to go in for the kill, it may not be safe, and it basically ends up, I think, with a lot of standoffs, and they're not really sure if they should go in for the kill. You can just watch one guy in particular, and you can see him avoiding all the other guys, but also trying to go in to kill. Because if they don't kill, then they die. They die of starvation. So yeah, makes some sort of intelligent behavior. I was thinking of adding bullets, which they could pick up and shoot at each other, just to make it maybe a little bit more interesting. But this is basically just a proof of concept, and I think it worked pretty well. So thank you for watching, and have a good one. Actually, wait a second. I think I'm going to put the download link in the description eventually, so you'll be able to run it on your own computer. And you'll find that when you first open the program, it'll ask you to enter the constant cost, or the movement cost, which is the amount of energy that they move, that they lose energy, like I said, proportional to their movement, the constant amount of energy that they lose, and the standard deviation, meaning just basically how much do they mutate every single time they get copied. So if your standard deviation is too high, then they never end up settling on a good configuration for their network, basically, because it just keeps on mutating too fast. Sort of like, imagine if a whole bunch of people had a bunch of radiation poisoning. You could have kids, but their DNA would be too messed up for them to survive. So instead, you have to have a relatively small mutation rate. But if you make it too small, then they'll learn too slowly, and maybe the population will get too homogeneous. Since they're making perfect copies of each other, maybe they'll all start behaving exactly alike, and that wouldn't produce much interesting behavior. So yeah, you can enter basically the mutation rate, the constant cost, and then you start it. If you put the constant or the movement energy cost too high, then basically there's a chance that if you put it at 2, they're basically guaranteed to at some point all die without being able to make copies of each other, because they just all starve at once or something. And so you'll find that you'll come back to the simulation and play it, and everyone's dead. So you just kind of wasted a bunch of computer power there. And but if you put the cost too low, then they'll come up with a very boring way of killing each other, which doesn't involve any intelligence. They'll just fly across, or they'll all just stay still and never die and never evolve. So you have to add some kind of cost to life for them to do anything interesting. And this is the kind of behavior that it ends up producing. You can see it's sort of intelligent. They point at each other. They point in the direction that they move often. Maybe not exactly. Alright, now at 12 million steps, I think it's time to end this video. It only takes about a few minutes running at full speed for it to get to some sort of intelligent behavior, which is what you're witnessing right now. Yep, I said it several times. This is the end of the video, and I'm not joking this time. Thank you for watching. Please like and subscribe, or do whatever you please, and have a good one.